Welcome to a video review from Bruce Tuckman, Fixed Income Securities. This is topic 5, and we are in chapter 10, which is called The Art of Term Structure Models. The TSM stands for Term Structure Models, Volatility and Distribution. And if you're with me now in this video, I'm sure you realize that this is the fifth of a sequence of 5 videos that started in chapter 6. And so we conclude here a long sequence that is a big component of what's assigned in topic 5. Chapter 10 is a continuation of chapter 9 in reviewing the term structure models. Chapter 9 started with some basic models like Model 1 and Model 2, and now in chapter 10 we're going to pick up with Model 3. So the basic idea is to look at a few examples of more sophisticated term structure models. Arguably, those should be more realistic at the cost of some sophistication. And that's going to conclude the Tuckman section. We have several learning objectives, including a review of these term structure models. Model 3, Cox, Ingersoll, Ross, which in my opinion would be the most recognizable of the models. We see this a lot in the academic literature, and the log normal model as well. So we'll look at examples of each of those. You'll notice that we have a couple of quantitative learning objectives. They're essentially similar to what we saw in chapter 9, which is to say that for each of these term structure models is basically a function, a formula. There's really a drift. In general, there's a drift component and there's a random shock component with various features. And we want to be able to apply that model a forward step on a rate. Actually, with some assumptions, we want to be able to say, okay, given some assumptions, what would Model 3 predict for the next rate in the tree? Or if we did the simulation, which is basically just applying the formula that describes the model and understanding the features. For example, does the model assume constant volatility? Does the model contain mean reversion? So there's just a handful of features that we need to worry about. And especially later, it is possible to take a deep dive into some of these models. So practitioners in those areas can do so. However, as we get closer here, we get toward the end with some complexity. I will say that the testability diminishes greatly because the theoretical complexity increases beyond the point of what we see on a typical exam. So I wouldn't necessarily worry about deep mastery of the log normal model, for example. I would just be superficially proficient and able to, if given assumptions, model forward a rate. If we have an initial rate, what would be the rate? What would be the rate next month, given assumptions? If you can do that for each of these models, you basically have the mastery for the exam. Although, before I start with learning objectives, a repeat of the slide that I had in the previous chapter, which we've inserted and summarizes chapter 9 and 10. And I believe that I said there that if you understood this exhibit, you're at least 50%, you're at least 50% covered on these concepts actually, maybe more, because this is pretty dense and this is pretty much the set of models that we look at, right? In chapter 9, we looked at Model 1 and 2, and we started with Model 1, sort of the base case of a model that has no drift and constant volatility. You'll recall that D of R is the change in the short-term interest rate. These are models for a short-term interest rate. So all of these have D of R in common. And so we looked at models 1, 2, Holy, Basicek in chapter 9, and these are the models here. It's Model 3, the Cox, Ingersoll, Rand, CIR, and then a few variations of the log normal. This is the one that can get especially sophisticated, but I think if you want to have like a favorite here in terms of what we study for, and what I mean to say is most likely to be tested frankly, because it's most recognizable, that would be the CIR. I would make sure I understand that. And let me just note here that mean reversion component, right? The CIR has a mean reverting drift. And we see theta. Oftentimes, that's the Greek symbol that's used to denote mean reversion. Okay, and then as before, we had types of models here, and except for CIR, these are no arbitrage models. And recall, we said an equilibrium model basically is a model that returns for us as output the term structure. So, and therefore we would not necessarily expect it to match the observed market term structure. As usual, there's a model and then there's the market. And market prices, including market rates, are a function of non-fundamental factors. Supply and demand by itself creates technical factors that can induce a difference between a fundamental model and what we see in the market price. And then, but the no arbitrage model on the other hand, these take the observed term structure as an input, and therefore they do match the current observed term structure. So our no arbitrage models are informed by, they take as information what we observe in the market's term structure.